In this module, first you review the baseline extract, load, and transform architecture diagram. Second, you look at a common ELT pipeline on Google Cloud. Then you review BigQuery's SQL scripting and scheduling capabilities. Finally, you look at the functionality and use cases for Dataform. In this module, first you review the baseline extract, load, and transform architecture diagram. Second, you look at a common ELT pipeline on Google Cloud. Then you review BigQuery's SQL scripting and scheduling capabilities. Finally, you look at the functionality and use cases for Dataform. Extract, load, and transform centers around data being loaded into BigQuery first. Once data is loaded, there are multiple ways to transform it. Procedural languages like SQL can be used to transform data. Scheduled queries can be used to transform data on a regular basis. Scripting and programming languages like Python can be used to transform data. And a tool like Dataform simplifies transformation beyond basic programming options. In an extract, load, and transform pattern pipeline, structured data is first loaded into BigQuery staging tables. Transformations are then applied within BigQuery itself using SQL scripts or tools like Dataform with SQL workflows. The transformed data is finally moved to production tables in BigQuery, ready for use. This approach leverages BigQuery's processing power for efficient data transformation. With support for procedural language, BigQuery allows the execution of multiple SQL statements in sequence with shared state. This enables the automation of tasks like table creation, implementation of complex logic using constructs like if and while, and the use of transactions for data integrity. You can also declare variables and reference system variables within your procedural code. BigQuery supports user-defined functions or UDFs for custom data transformations using SQL or JavaScript. These UDFs can be persistent or temporary, and it is recommended to use SQL UDFs when possible. JavaScript UDFs offer the flexibility to use external libraries, and community-contributed UDFs are available for reuse. Stored procedures are precompiled SQL statement collections, streamlining database operations by encapsulating complex logic for enhanced performance and maintainability. Benefits include reusability, parameterization for flexible input, and transaction handling. Stored procedures are called from applications or within SQL scripts, promoting modular design. BigQuery supports running stored procedures for Apache Spark. Apache Spark stored procedures on BigQuery can be defined in the BigQuery PySpark editor or using the create procedure statement with Python, Java, or Scala code. The code can be stored in a cloud storage file or defined inline within the BigQuery SQL editor. Remote functions extend BigQuery's capabilities by integrating with Cloud Run functions. This enables complex data transformations using Python code. You define the remote function in BigQuery, specifying the connection and endpoint to your Cloud Run function. This function can then be called directly within your SQL queries, similar to a UDF, allowing for seamless integration of custom logic. The example here shows a Python function that gets a list of signed URLs pointing to cloud storage objects and returns the length for these objects. In BigQuery, we just need to register the function. We call it object length, then we can use it as is in SQL. Jupyter Notebooks coupled with BigQuery data frames facilitate efficient data exploration and transformation. This integration emphasizes the ability to handle large datasets that exceed runtime memory, perform complex data manipulations using SQL or Python, and schedule notebook executions. The seamless integration of BigQuery data frames and popular visualization libraries further streamlines the entire process. BigQuery offers the option to save and schedule queries for repeated use. You can save queries, manage versions, and share them with others. Scheduling allows you to automate query execution by setting frequency, start and end times, and result destinations. Dataform is recommended for more complex SQL workflows. Often there are needs to perform additional tasks after a scheduled query is executed in BigQuery. These include tasks such as triggering subsequent SQL scripts, running data quality tests on the output, or configuring security measures. In an ideal situation, these actions can be automated, ensuring data pipelines remain efficient and reliable. Dataform is a serverless framework that simplifies the development and management of ELT pipelines using SQL. Dataform enables data transformation within BigQuery, ensuring data quality and providing documentation. This approach streamlines the process of moving data from source systems to production tables in BigQuery, making operations more efficient and manageable. Dataform streamlines data operations in BigQuery by unifying transformation, assertion, and automation. Without Dataform, tasks like defining tables, managing code, testing data quality, and scheduling pipelines would be time-consuming and prone to errors. They could also involve multiple tools and manual processes. Dataform simplifies these tasks within BigQuery, improving efficiency and data reliability. Dataform and BigQuery work together to manage SQL workflows. With Dataform, developers create and compile SQL workflows using SQL and JavaScript. Dataform then performs real-time compilation, including dependency checks and error handling. Finally, the compiled SQL workflows are executed within BigQuery, enabling SQL transformations and materialization either on demand or through scheduled runs. Development using Dataform utilizes workspaces containing default files and folders. Key folders include definitions for SQLX files and includes for JavaScript files. The gitignore file is used for managing Git commits. Developers may also use package.json and packagelock.json for handling JavaScript dependencies. The workflow settings.yaml file stores project compilation settings, and custom files like readme.md can also be added. The SQLX file structure provides a clear framework for organizing SQL code and associated tasks. It begins with a config block for metadata and data quality tests, followed by a JS block to define reusable JavaScript functions. The pre-operations block handles SQL statements executed before the main SQL body, which defines the core SQL logic. Finally, the post-operations block contains SQL statements to be run after the main execution, ensuring a structured and efficient workflow. SQLX development streamlines SQL code by replacing repetitive patterns with concise definitions. The code example demonstrates how a complex case statement for categorizing countries can be replaced with a simple function call, mapping.regionCountry. This approach improves code readability and maintainability by reducing boilerplate code and promoting reusability. With Dataform, mapping.regionCountry. This approach improves code readability and maintainability by reducing boilerplate code and promoting reusability. With Dataform, table and view definitions should be created in a specific manner so that they can be compiled into SQL statements. Key configuration types are declaration for referencing existing BigQuery tables, table for creating or replacing tables with a select statement, Mental for creating tables and updating them with new data, and View for creating or replacing views, which can optionally be materialized. Dataform offers assertions to define data quality tests, ensuring data consistency and accuracy. Assertions can be written in SQL or JavaScript, providing flexibility for complex checks. Operations allow you to run custom SQL statements before, after, or during pipeline execution. These two options enable custom data transformations, data quality checks, and other tasks within your workflows. By combining assertions and operations, Dataform empowers you to create robust and reliable data pipelines in BigQuery. Dataform provides two methods to manage dependencies: implicit declaration and explicit declaration. Implicit declaration is when you reference tables or views directly within your SQL using the ref function. Explicit declaration is when you list dependencies within a config block using the dependencies array. It is also possible to use the resolve function to reference without creating a dependency. Dataform allows you to compile user-defined table definitions into executable SQL scripts. The sample code shows a customer details table being created or replaced based on a customer source table using a select statement. Dataform manages the dependencies between these tables and orchestrates their execution within a workflow. This process streamlines data transformation and ensures efficient data pipeline management. Dataform's SQL workflows are best visualized in graph format. The sample workflow starts with a declaration of customer source followed by a customer intermediate table, likely derived from a source system as a pre-processed data source. Next, customer row consistency applies assertions for data quality checks. The graph then splits into two paths. In one path, an operation named customer ML training is invoked. It performs operations on the validated data. In the other path, a view named customer prod view is created. There are several scheduling and execution mechanisms for Dataform SQL workflows. One path is through internal triggers. These include manual execution in the Dataform UI or scheduled configurations within Dataform itself. The other path is through external triggers. These include tools like Cloud Scheduler and Cloud Composer. Ultimately, all workflows are executed within BigQuery, showcasing its central role in this process. In this lab, you use Dataform to create and execute a SQL workflow. First, you create a Dataform repository. Second, you create and initialize a Dataform development workspace. Then, you create and execute a SQL workflow. Finally, you view execution logs in Dataform to confirm completion.